Hello, calculus class. Today we're going to look at our last set of what I like to call factual integrals. In other words, those integrals which you should memorize. So I think it's going to be a pretty simple lesson. It's just looking at other known different derivatives and finding their antiderivative basically by going backwards. We might apply some u substitutions as well, but I don't think there's going to be a whole lot else more to this lesson. Okay, so these are our last group of factual integrals which we need to be responsible for. Alright, so I think you should already be able to tell me what the integral of e to the x is, even though we haven't done an example like that before. Why? Well, because you know what the derivative of e to the x is. Remember, it's that function, when we look at e to the x, that exponential growth function, like this. Remember, the e to the x is the function that is perfectly aligned so that the slope of its tangent line at each spot is the same as its y value at that spot. So remember that the derivative of that exponential function is equal to itself. So if you take the integral and find the antiderivative backwards, it's still going to be equal to itself, except of course you could have any constant added on there, and when you took the derivative that would go to 0. Alright, so what if you have an exponential function based something else, like, I don't know, 1/2 to the x power? If you remember that that's just going to be, this is an exponential decay example, 1/2 to the x power, for instance. But its derivative isn't exactly itself. You kind of need to multiply it by some kind of stretch or compression factor to get it to go back to that exact shape of e to the negative x in this case. So remember, you just need to kind of compensate. Let's think about our Zen method for integrals and compensating. So we need to compensate for that stretch factor like so. So we're going to still get that exponential function back plus c, but in order to compensate, we're going to, instead of multiplying by the natural log of the base, we're going to divide by the natural log of the base. So really, I guess that 1 that I wrote is kind of unnecessary. Let's just take it out. And there you go. So pretty simple. It's just the derivative in reverse compensating for the multiplication by division. Okay, so these other three we haven't seen for a little while, or not too often anyway, but hopefully you're also thinking about them with derivatives. If you remember, this is the derivative of, you guessed it, arcsine. So the antiderivative of something with a square root of 1 minus a quantity squared in the bottom is going to be arcsine. Now we're going to practice a lot of different varieties of these arcsine and other arc function integrals in the next lesson, but I'm just going to present them right now so that we can focus on the more subtle aspects of algebraic manipulation in the next lesson. So hopefully you also remember this one. This is one of the most common integrals in the applied world, I would say. I've definitely run into it a whole lot of doing engineering and physics work myself. So this one you should remember is arctangent, sometimes called inverse tangent, right? So I could have called this inverse sine, I could call this one arctangent, just different notations for the same phenomena. Okay, so this last one, hopefully you're kind of getting the pattern here, is then arcsecant. Remember, you need to memorize these exactly the right way. You can't go x squared minus 1 here. Arcsine is the integral of 1 over the square root of 1 minus the thing squared, and arcsecant has that backwards. So remember not to mix those up, and you should be solid. So you might be wondering right now why I didn't do like arccosine and arcsecant, arc cosecant and stuff like that. Well, it's because, oh, I forgot my plus c here, better put that in. It's because those are not very common. Like, you can pretty much always just turn those into one of these. For instance, technically, the antiderivative of negative 1 over the square root of 1 minus x squared dx, technically, that's actually equal to the inverse cosine of x plus c. But you can see how easy it is to just take this minus, move it out here, and then that's really just negative inverse sine of x plus c. Okay, so you can see that you really only need to remember 3. Alright, let's do some basic examples, at least with our new exponential integration rules, and we should be set. So this is one that I'd like to do with the Zen method. I'm going to think about u, or my inside function, being 3x plus 1, and if I took a derivative, I'd have the chain rule, which would tell me times 3, so my antiderivative, I'm going to have to undo that times 3 by dividing by 3. And the antiderivative of e to the x, or e to the stuff, is still e to the stuff plus c. If you didn't like that, then go ahead and write out the full u substitution. I'll just do that really briefly. So you'd say this. You'd take the derivative, that's 3dx. You'd move your 3 over here. And you'd say that this is equivalent to e to the u, and dx is du over 3. So that's 1/3 e to the u plus c, and u, of course, was e3x plus 1. So you can see that I get the same answer either way. I think this one's easy enough to apply the Zen method, as my teacher, Dr. Barnett, used to describe it. So here, I think I personally would also apply the Zen method, but you guys might not be that comfortable yet, so I'm going to show the substitution. So I'm going to say u is the inside function up there in the exponent. Take a derivative. It's negative 2x dx. And you can see that I see the x and the dx right there, so I'm going to say du over negative 2 is x dx. I'm just going to come over here and say that this is equal to, I'm going to pull my 5 out in front. Then the x dx, that's du over negative 2 from my substitution. And I'm just left with e to the u as well. So pull that also out in front, and we have negative 5/2 integral of e to the u is e to the u. So exciting. So that's going to be this, e to the negative x squared plus c. So you can see if you're thinking Zen method, you just think about this, and you think about, okay, I'm going to have times negative 2x. I've already got my x, so I just need to divide by negative 2 to get rid of that, and you could think about it by Zenning it right here and get the answer straight away. I think number 3 is another great example of where the Zen method could be applied. If you also like to think about lurking, this is what I like to call a lurker. It's because if I make this u, du is lurking right there, isn't it? Well, I should say negative du. If u is cosine, the derivative of cosine is negative sine. So all I need to do is put this negative out in front, and I'm good to go. So this is really just the integral e to the u negative that du, which is, of course, negative e to the u, which is negative e to the cosine of x plus c. So I wasn't very formal about my substitution on that one, but hopefully I needn't be by this point. Alright, let's look at 2 more before we call it quits for today. So this guy, I think we're going to see lots of integrals with different combinations of e to the x. These e to the x combo type of integrals are big. They are important as we move into Calc 2, so let's just keep in mind that you want to pay extra attention to these ones. So you might not know what u is on this one right away, so I'm just going to try to hurry this video up, so I'm going to guess it. We've seen lots of integrals where u is the bottom, because the bottom is a very popular inside function. So if you try that on this one, I think it's going to come out. Let's see. So if we do u as that, then du is 0 there, and e to the x stays the same, dx. Oh, it's lurking right there. So this is really just another lurker. It all depends on your perspective. The key is that you make these your own. However you do that is kind of up to you. So you know what? I'm going to erase. I'm going to pull that 3 right out in front. It's kind of distracting me. I'm going to get rid of it and pull it out there. So now on top I have the u du right there. Or excuse me, that's just du. It's not u du. That's just du. And on the bottom I have u. And I think last week we learned how to do that. That's 3 times the natural log of u plus c. So our final answer is 3 times the natural log of that stuff plus c. There we go. Alright, one last problem, and you guys should be good to go to work on this pretty simple assignment. So this time we have an exponential function, pretty boring, but it's a different base, so I have to remember to compensate for that base. If I take the derivative, just reminding you, if you take the derivative of 2 to the x, you should have memorized that that's the exponential function shifted by this scale factor. So when I integrate, it's going to be the exponential function divided by that scale shift. And that is pretty much all she wrote on this one. So you might be asking at this point, why am I not doing some examples with these arc function rules? And I think that we'll do some examples, both simple and sophisticated, in the next lesson. I'll see you then.